Right, testing, testing. Doing this one a little bit different. My headphones have no juice. I guess the case, didn't have any power to charge them. Testing, testing, and just making sure I can hear the audio. Okay, so that is the proper audio. Let's see. Done. Screen. Okay. All right. So greetings, YouTube. So this presentation serves as the last of the new material for our Calculus for Business spring of 2022, right? So we are wrapping up chapter 4 on integration, and we're going to be working on section 4.6 integration techniques. This is called integration by parts. Let's finish this out, and then we'll do some final remarks as far as what to expect over the next couple of weeks. So this is over section 4.6, integration techniques, integration by parts. A couple of objectives. We like to evaluate integrals using the formula for integration by parts, and then solve applied problems involving integration by parts. Okay. So we have this theorem 7. It says this is the integration by parts formula. So given we're trying to evaluate an integral, we're going to have to break the integral up into 2 parts. We're going to have a u and a dv, right? We're going to show how we arrive to those. But once you identify your u and the proper u and the proper dv, then the integral of u dv is uv minus v du, the integral of v du, right? So that kind of has a rhythm. The integral of u dv is uv minus the integral of v du, right? Okay, so I know that's kind of a mouthful. Let's just see this in action a few times to kind of get to the bottom of this technique and how it works. So a few tips on using integration by parts. If you've had no success using substitution, so first we try substitution, then try integration by parts. Use integration by parts when an integral is of the form f of x times g of x dx, right? So you have one function times another. Match it with an integral of the form u dv. That's fine. By choosing a function to be u, where f of x can be differentiated, and a remaining factor to be dv, which is going to be g of x dx, where g can be integrated, then find du by differentiating, and v by integrating. If the resulting integral is more complicated than the original, make some other choice for u and dv. To check your solution, differentiate, right? So let's see this in action. Evaluate, right? Okay, so let's do this. Let's let our u, let me see. I think you want something to be easy to differentiate. So we're going to let u be ln x. So that means our du would be dx by x. And then we're going to let dv, and let's put dv down here. We're going to let dv be dx, right? And the integral of dx, so that means our v is x. So, because that was easy to integrate. So now, the original, we had what? ln x dx, right? So the blue goes with blue, purple goes with purple. Now, if we're applying the integration by parts formula, so that's, it should be uv minus, so this is u dv equals uv minus v du, right? So we got to say u, so that's going to be, here's our u, and then our v is x. Then we're going to say minus the integral of, that was uv, so now we're doing v du. So it's going to be the integral of x dx over x, right? Which we can simplify. It looks like these guys cancel, right? Then it looks like we have x natural log of x minus the integral of dx. Integral of dx is what, x? So it looks like we get x ln x minus x plus some constant. Okay. And then we can check that this works if we differentiate. If we take the derivative, we should be able to get back to the original. I'll check it. I don't know who that is. Okay. Just glad it didn't pop up on my tablet and throw everything off. Okay. So like for instance, this derivative, this is gone. This will go to 0. This will be -1. Here we would have to do what? The product rule. So the first times the derivative of the second. Let's just write it over to the side. So the derivative of ln is dx is basically 1 over x. So that's going to be divided by x. So the first times the derivative of the second plus the second times the derivative of the first -1 plus 0, right? So then we can see that this is going to be canceled by this, and we finish with our desired result. All right, so we can be confident in this result. And again, what this was just a quick check by taking a derivative. So we got x ln x minus x plus a constant. X ln x minus x plus a constant. Let's try another one. All right, integration by parts. Quick check. I'll leave that as an exercise for you. All right. Let's see. Okay. So let's see. We're gonna let you. We can still leave it as ln x. So that means our du would be what? Dx over x, right? And then we need to identify our dv, something that's easy to integrate, which was x dx, and the integral of that. So that means our v is going to be x squared over 2. Right? Okay, now if we make these substitutions, so we have the integral of our u. Let's see what's a more simple way to write this. So we have this natural log of x times what? X dx, right? This is what we started with. This is going to be equal to u, which is ln x times our v, which is x squared over 2, minus the integral. Let me see if that's u dv, so it's v du. V du. So v is going to be x squared over 2 times du, which is going to be dx over x. All right. Okay. So I think we got past the hardest part. The first part we can kind of rearrange it. I'm going to write it as 1/2 x squared ln x. We're going to say minus. So x squared divided by x. Let's see. That x is going to turn this into a 1. When you integrate that, it's going to become x squared over 2. So then it's going to really become x squared over 4. So you're going to get x squared over 4 plus some constant. I think if we can like condense this or simplify it some way. Because you could factor out 1/2 x squared from those two terms, but I don't think that really helps us any. So I'm going to go with this, and let's see how do we do it. And again, we can always check by taking a derivative to see if we get back to the original. I'm just going to use my prepared notes. 1/2 x squared ln x minus x squared over 4 plus a constant. There it is. 1/2 x squared, 1/2 x squared ln x minus x squared over 4 plus a constant, right? Let's go back and read through and see if they did anything different, right? So first, let's examine several choices for u and dv. Let u be 1. No, we already know that doesn't work, right? So we're just gonna let that be. Let u be, now they tried x ln x, but I think that one, this integral seems more complicated than the original, so I'm just gonna let it be, right? They just tried a different u and a different dv, but that didn't seem to work either. We got lucky. We chose the proper u and dv off the rip, so we were good to go. So let u be this, and the dv was this. So if u is this, then du is this. If dv is this, then v is this, right? So then using integration by parts, long story short, they got the same thing that we got. Okay. Let's try another one. We got lucky. So you want your u to be something that's easy to differentiate, and you want your dv to be something that's easy to integrate. Okay. So with this one, I'm going to say let u be, I'm going to let u be 5x plus 1, and I'm going to let my dv be x dx, right? So then if that's my u, then my du is going to be what? 5 dx. Okay, so we got to account for that 5. We just need dx. Oh, wait a minute. Yeah, I think we're okay. So since we just need dx, no, sorry, no, we're good. Let's keep going. So we got our u and our du, and then our v, if we integrate, it's going to be what? X squared over 2, right? So the original, we have the integral of what? The square root of u. All right, integral of the square root of u dv. All right, because see, now you can see your you know, u dv. Okay. Wait a minute. Can we do this? Because I feel like this doesn't have the proper form. Unless we do a second integration by parts where we got like u prime is that square root of u. Do we have to do a double integration by parts here? Because if we let u be the square root of all of that stuff, we're going to get, I mean, we can find that, we can take that derivative. We're going to get the 1/2 times this times 5. Because I feel like what we chose just doesn't have the proper form. That's my only hesitation. So I feel like our dv is good, but I think we need to change the u. So let's change that u. I'm going to scrap this for right now. And I'm going to let my u be the square root of this guy. Now I'm going to try this. If this doesn't work or if it seems worse, we might have to do integration by parts twice. Which I think, I'm thinking that's what they want. Arms, column, this and the other. I keep getting so many wrong numbers. I'm like, I don't know who got what. So if that's our u, then when we go to find du, it's going to be 1/2 5x plus 1 to the power of negative 1/2 times 5, right? Because you got to say derivative the outside times the inside. Okay, we can let that be for now. Hopefully it doesn't make it too bad. Let me think. U dv uv minus v du. Actually, that does make it kind of hard. So I'm going to go back to what I had before, and I got this notion to do something twice, to do the integration by parts twice, the du here is 5dx, right? And then when we make our substitutions, we got the integral square root of u dv, right? But this doesn't have the proper form for us to do integration by parts, right? So I'm tempted to just do it again, just do integration by parts again. So I'm going to consider u prime. I think that's what they want. Let's let u prime be the square root of u, right? And our dv, I think you can say as is. Our dv, let's call it dv prime. It can be dv, right? I'm going to just leave it kind of like that. So then our du prime is going to be 1/2 u to the minus 1/2 du. Let's keep going. And the integral, so our v prime is what, just v. Ooh. Okay, so let's try that here. Hopefully this isn't hopefully this works. I don't know. So then u dv. So now at this stage, I'm just going to kind of do it like this. This is going to be the integral of u prime dv prime, right? So then this is going to be equal to uv. So that's going to be v times the square root of u minus the integral of v du, or v prime du prime, right? So v over 2 root 2 times the square root of u du. Let me see, what's our v? What's our u? And what's our du? Maybe we can make our substitutions here and we might be okay. Let's keep going. Let's just try. Let's make our substitutions here and see, because it's trying to integrate that guy. I feel like this is working. Let me think about this. Because if you substitute in, your v is x squared over 2, your u is 5x plus 1. I feel like this isn't working either. Let me think about it. Our u is that. Okay, I'm going to call an audible. Let's look at the notes do. Okay, dv. We didn't even consider trying to integrate that. Okay, let's try that. So I was totally avoiding trying to let this be your dv, right? Because I just saw that square root and I automatically didn't even consider it. So, and I was getting stuck because I tried different ways of letting this be the u, but I never tried, well, let this be your dv. So let's let this be the dv, and then let's give it a go from there, right? So whatever we tried didn't work, right? So now let's do this. So we're going to say let u I think u is going to be what? X. And we're going to let our dv is going to be the square root of 5x plus 1 dx. Okay. So if that's the case, then our du is going to be what? Dx. And our v So if you integrate that, that's what? Something to the half. So we're going to have 5x plus 1 to the power of 3 halves over 3 halves. And I feel like there's something else. Because this derivative, I think we need to say like divided by 5. Because if you take the derivative of this as is, the 3 half comes down, they cancel. You get the 5x plus 1 to the half. But then you got to say times 5. So I think we need to divide by 5. So I'm going to say times 1 over 5. So now when we take the derivative, the 3 halves come down and they cancel. We get our 1 half in the power. So we get 5x plus 1 to the power of half times 5. And so then they cancel each other out, right? Okay. So if this is proper, so now let's do our substitutions. So then we're going to have the integral of u dv, this times that, okay? And what I'm going to do here, I'm going to write it as this u dv, okay? This is going to be equal to, I'm going to do this, u v, write out the formula, minus the integral of v du, right? And then make our substitutions. So u is going to be x here, and let's keep the colors consistent. So we're going to have x, and our v is all of that. If you flip and multiply, so then you get 2 times this 5x plus 1 to the power of 3 halves over 15. Right? So that's our uv. We're going to say minus the integral of v du. Okay, I think we're almost there. Let's keep going. So v, let's leave it as 5x plus 1 to the 3 halves over 3 halves times 1 over 5, right? And then du is just dx. Okay, let's see. Can we integrate that? I think we can, right? Because I think we literally just did it. So the 1/5 can go in front. I'm going to kind of just let that first part stay as is. Let me see. That's going to become what? 5 over 2. So this is going to be minus, we got this 5x plus 1 to the power of 5 halves over 5 halves. And I think it's times 1 over 25, because I think we had to incorporate another 1/5, 1 over 25. And we can check by, if we take the derivative, the 5 halves comes down and cancel, we get 3 halves times 5, and that produces the 1 over 5, right? I think we've gotten rid of all the integrals. This is a funky one. On the left here, we still have our 2x, 5x plus 1 to the power of 3 halves, all over 15. I think that's it. I think that's as far as we can take. I think that's the best we can do. Oh, we're going to cross our fingers on this one. That one was nasty. Okay, I'm going to go with this. And I want to look at the notes to see what they did, if they got the same thing or not. Now, we can, because like you can flip and multiply, so that would be what, 2 over 125, and you got your 2 over 15 there. But I feel like this is far enough just to get the point. Okay, let's see what did the notes do. Okay, so let the u be x, the du was dx, dv was this, and then you see the 2 over 15. That 2 over 15 is a good omen. I think this is it down here at the bottom. Now they got 2 over 15. I think we got the 2 over 15. If you flip and multiply 5 times 125. There's a 2 there. Did they get a common denominator or something? Are we missing something? I think we forgot to distribute that 2 over 15 at some point. Right there, the V is 2 over 15. Did we get the proper V? We got our 2 over 15. Yeah. Or 1 over 15. Oops. One half, 3 halves. Yeah, 2 over 15. We got it. There's a 2 over 15. Oh, but I think over here, no, you add 1. I think we forgot the 3, right? You add 1, so it's going to become 5 halves. So I think we forgot that 3 halves there, right? Right here, I think we forgot to keep that original 3 halves. That's why the numbers were a little off. So then 15 over 4. So you get 4. You get 4 over 15 times 25. 1 over 25. Yeah. So we just were we definitely missed that red 3 halves. That was the only thing we were missing. And that accounts for this guy right here. Everything else is fine. That's a doozy. I knew it was this guy when I first saw it. I was like, I knew that's the challenge, but it didn't even dawn on me to let it be your DV, right? That was the challenge there. I kept trying to have this term over here somewhere, right? And so it wasn't that this was supposed to be over here. This was supposed to be over here for the DV, right? So, but we got it. It's kind of funky, but we got it. You know, we don't really have control over that. We just have to keep trying. Okay, so we're going to kind of let that be, take a breather for a moment. Quick check I leave as an exercise for you. All right, I think we did this one. Let's just do it again. Integration by parts, right? Can we do some? I don't think it's substitution here. Let's try integration by parts, right? So if we let u be the natural log of x and our dv be dx, then that means our du is going to be dx by x, and our v is going to be what? X. Okay. So then we're going to evaluate the indefinite integral first. So then this is going to be the integral of now ln. So ln x dx. So we can identify the u and the dv. It's going to be u, which is this guy, times v, which is this guy. I'm just applying the integration by parts formula right now, minus the integral of v du. So x dx over x ends up just being the integral of dx. Okay. So then this becomes x ln x minus x, and we want to evaluate that. Now we're ready to put the limits of integration back. We want to evaluate this as x goes from 1 to 2. So then when we plug in 2, it's going to be, well, you can basically say 2 natural log of 2 minus 2, and then minus the natural log of 1 is 0. So minus a negative 1 essentially becomes plus 1. So then the exact result should be, you could even say the natural log of 4 minus 1, and then whatever the calculator says. Let's go ahead and do that, crunch that number. Natural log of 4 minus 1, nope. Natural log of 4 minus 1. We get 386 approximately. Okay, let's see, how do we do? Let's copy, okay? Let's see. 386, you see it there? Okay, let's keep going. I'm trying to finish this in time for class. I still got a little bit of time. So this example, It says the rate of change in the population of bacteria T hours after antibiotic treatment begins is estimated by this guy here, where P prime is the rate of change of the population in thousands of bacteria per hour. Assume that when the treatment begins, the population consists of 1.5 million bacteria. Find the population of bacteria after 24 hours of treatment. What is the total change in the population from 24 to 36? Find the population after 24 hours of treatment. Let me see. The rate of change of the population of bacteria T hours is given by this. So if we want, can we just, I mean, let's find the population of bacteria after 24 hours. So let's just integrate, right? We take that, let's find the integral and then evaluate it when T is 24. And then for the 24 to 36, it's the definite integral as T changes from 24 to 36, right? So let's try that and see if it works. Because that's what I'm getting out of it. That's the sense that I'm getting, right? So let's start here. So basically it sounds like they want us to find the integral of T e to the negative 0.04 T. Okay. So since we're doing integration by parts, let's let U, let's let U be e to the negative 0.04 T, and this needs to be a dt right here. And then so we can also let our dv, something that's easy to integrate, be T dt. So then that means our du will be itself e to the negative 0.04 T times the derivative of the power, sometimes a negative 0.04. I'm gonna give myself some space. This is basically just multiplied by this guy here. Kind of trying to keep my alignment consistent, but it's a little bit weird with this one. And then our V, but the integral will be T squared over 2. Okay. So then the integral of our U, so this is going to be what, the e to the negative 0.04 T times what, T dt. So that's our U dV. This is going to be equal to U, which is this guy, times our V, which is this guy. And we're going to say minus the integral of V du. Okay. Does this help us? Or is it making it worse? We're integrating. You know what? I think this is making it worse, right? Because if we do V du, it's like a worse version of what we started with. So I'm going to choose a different U and a different dV. I want to get rid of that, and I want to get rid of this. Okay, so I think we did E was our U, so now we're going to let U be T. So then that means our du is going to be dt, right? So now with this, that means that our dv would have to be this guy, this e to the negative 0.04 T dt. And then that means the integral of that guy, the integral of E is itself. but then we got to say divided by this, right? So just check by taking the derivative. The derivative of v is itself times the derivative of the exponent, and it's going to be canceled by this guy, and we'll finish with the desired result, right? So this feels better. So now when we do our integration by parts, so our u times dv e to the negative 0.04 t dt. This is going to be equal to uv, so u, which is this guy, times our v, which is all of this, and we're going to say minus the integral of v du. Okay, so the integral of this e to the negative 0.04 t over, and du is just dt, right? See, now you see how this was simplified. Like we got rid of a term, right? So we're going in the proper direction. So I think now we can just integrate like normal, right? So we're going to bring everything else down. So we're going to keep this t e to the negative 0.04 t over negative 0.04. Double negative, we can go ahead and put plus 0.04. The integral of e is itself e to the negative 0.04 t, but then we need to say divided by negative 0.04, right? So basically, these guys cancel. That makes the negative persist. And then we just need to basically plug in when t is 24, right? So if we kind of simplify this a little bit more, we get the population of p of t. We get negative 0.04 t e to the negative 0.04 t. We're going to say minus e to the negative 0.04 t. We could factor that out, and that would give us a 1. Okay, so then I think part A was asking us to find p of 24, right? Whew. All right, so let's plug it in when t is 24. So negative 0.04 times 24 times what? E to the power of negative 0.04 times 24, okay? Then we're going to say minus E to the power of negative 0.04 times 24. Okay. What is negatives? I was a little bit leery about that. Let me see. Find the population after. Thousands of bacteria per hour. So if we started with 1.5 million and we're down, I think this just means that we're down. If I can get it to come back up. And these are, so we need to multiply this by 1,000, right? So move the decimal to the right by 3. So 750. So then what we need to do is say 1,500,000 plus that answer times 1,000, right? Because basically we're deducting that these are number of bacteria in thousands per hour. So we take that answer times 1,000 and subtract it from the starting amount. And so after 24 hours, it looks like we have about Is that right? Something's still off. 1 times 1,000. 1, 2, 3, 750. 1 million. We get like 1,499,249. So maybe let's okay, let me look and see what the notes did and compare for part A. Right? 625. Okay. Are we missing that 25? I feel like some things are off. Let's see. Okay. So let U be T, so dV be this, so du and this, -1 over 0.4 E. We got all of this, right? So then P of T, right here. Okay, we can confirm some of these numbers. Right here. Let's see if we get this negative. Yeah, we got the negatives. So let's make sure we get the -25 and the -625, right? If we got those, then we know we're fine. What are we missing? Oh, okay. I see what I did wrong. I just moved it up. I didn't divide it, right? That's what I did wrong. Right here. I had divided by 0.04, and then for some reason I just moved it to the top. So I needed to multiply. I think these guys cancel. 625. Is there something else we're missing? I think that's okay. But it looks like we're missing something here as well. So, for instance, if we say 1 divided by 0.04, you see the 25. So we got the 25 here. Let me think about this. You know what? I bet you I did that same thing I did last time where I forgot to keep that. I see my mistakes. Let's clean up what we have, right? What we have is not far off. So, for instance, like, why did I multiply? For some reason, I moved those up, right? Incorrectly. Okay, let's go back and clean these up. The first term is fine. The second one, this guy needs to be down here. Like, I don't know why I did that. I think I'm just tired and I don't want to do it. I really think that's what it is, right? But right here, this is really this guy right here. So we got to say divided by another 0.04. So the double negative becomes positive. So basically it becomes 0.04 squared, right? So then, right here, we got to fix this guy. So for instance, when you divide by 0.04, that's a negative, because it's 4 over 100, so 100 divided by 4 is 25. So this is a -25. And then over there, we had divided by 25 squared. Right, and I think that this negative persists. I may have changed it before what I had before. This negative persists. We get a double negative on positive, so that negative persists. And this guy right here, when we divide by 0.04 squared, that's the same as multiplying by 625. Right, I think we got the same thing there. Now I think we're back on track. And then let's plug this into the calculator because I think what we had before may be a little bit off. Oh, also trying to rush. I got like 30 minutes before class starts. I'm trying to finish this before class starts. Okay, well, I think we're there. So then we get -25 times what? 24 E -0.04 times 24. We're going to say minus 625 times E. Nope, that's not E. Come on. -0.04 times 24. Okay. So then if we say 1,500,123, we're going to say plus that answer times 1,000, because those are in thousands of bacteria per hour. I feel like this is a lot better result, right? So I want to say we get approximately 1, 2, 3, 1, 2, 3. So 1,030,956. I'm going to put 0.215 bacteria. Okay. All right. I feel better about this. I think I'm just tired because I did the previous section and this one back to back. I think I'm spent. And I usually just don't go back and do edits and stuff like that. I just because it's important to see to see that thing of making mistakes and kind of being exhausted. All right. So after 24 hours, we get about 1 million bacteria remain, right? Okay, so we cleaned that up. We confirmed those numbers. We got the same thing. Define C. Oh man, I totally did forget about C. Man, I am off. And did we at least write C? We forgot to write C and everything. Okay, so we got to get rid of this, right? So when we integrated, we needed a plus C right here, right? And then to find that C, they give us 0. Well, I think, okay, honestly, I think what we did, we kind of found it already, but for instance, when T is 0, so let's go ahead and let's just do that. Let's just do the proper thing. So we know that P of 0, right? The first term is going to be 0, so we can just let that go because this guy forces it to be 0. And then we plug 0 into the second term, get this 625 e to the power of 0 plus c equals 1,500,000. Okay. So then that's gone. So then we add 625. So then it looks like C is 1 million. This might be, I might be getting my units off here. Man, I am like struggling with this one. 1,500, right? Okay. So right here, we're gonna keep the units the same. Instead of writing that all the way out right here, this needs to be 1,500. So now when we add the 625, what is that? 2125. So it looks like our population is going to be negative 25 t e to the negative 0.04 t minus 625 e to the negative 0.04 t plus 2125. And you just got to be aware that your final answer is in thousands of bacteria. Right, so you still need to multiply by 1,000, right? Let's try this one more time. I'm just going to type it in here. Negative 25. Actually, I'm going to go over here to my y equals. Negative 25x times e negative 0.04x minus 625 times e negative 0.04x plus 2125. Okay. So then what I'm going to do is call on that function when t is what, 24, right? So that way, okay. So populate the bacteria is growing. I hope this makes sense. Let's see. 655 956 215. Okay. Here we go again. Let's try this one. Paste. Okay, let's see. So we went back and solved for our C. We got that 2125. Okay. Now we got it. 956, right? So yeah, just definitely nuanced. I forgot about the C. I just forgot about it. Because like when you integrate, you still got to account for the c. That's why they gave us an extra piece of information about the starting amount. So that way, when t was 0, we can solve for the c and then get the proper form. So then, I'm just gonna, for the sake of time, because I'm kind of burnt. The total change. So they wanted us to integrate from 24 to 36. You can honestly, yeah. So right here, we can use the result that we got. So we got a result that we just used for 24. I think the 24 is what we just, this is the one we just did. So then we can go and plug in when t is 36. You get this result for 36. This is the result we just got. And then you just subtract them. And that's where this comes from, right? So the total change in the population between 24 and 36 hours is approximately 107,000 bacteria, right? But it was just piggybacking off of the result that we had just gotten. I got maybe 10 minutes. I'm trying to finish the time for you guys. Let's see. Hopefully I'll be able to. Evaluate this to find the area of the shaded region below. Okay, let's do integration by parts. Now, usually with these, you're gonna have to do it a couple of times. So let's let me give myself some space. So I'm gonna add a page. Let's get a copy of the original. We got this integral from 0 to 7, x squared e to the negative x dx. We might have to do it a few times. Now, I think with this one, actually, there was a table, right? I think I'm going to piggyback off of this because I am kind of burnt. Because like, for instance, what you would do, I would let the u be x squared and the dv be this guy, right? That's the integral. So the integral of this would be itself divided by, let me think about that. Divided by -1, right? Because if you take the derivative, it's going to be itself times -1. So you got to divide by -1, right? So if this is your u, when you take the derivative, it's going to go from a power 2 to a power 1, but then you're going to have to do integration by parts again. It looks like you're going to have to do integration by parts twice. So again, for the sake of time and just because I'm burnt, I'm going to piggyback off the notes. So right here, see? So let u be x squared and du be 2x. And then this integral, right, we said was negative of that guy, okay? So then you're going to do your uv times your vdu, these guys. And see, you're going to have this term that persists. So here's your uv minus your vdu. The 2 you can honestly pull out in front. And so now you got to do integration by parts again. They said let the u be 2x from here. And your dv it kind of is the same thing. So then you get the same v. And now the terms are disappearing, right? So the x, now the x is a constant. So then you do integration by parts again. And like I already felt it coming. I was like, nope, I'm not doing it again right now. Right? And then we get something like this, right? Let's see. So uv minus v du. See, now we only have this e to the x term. So now I think we can just integrate that as is. And ultimately get here. So we can substitute this solution into the formula on the last slide. You get something like this. And then you do the limits of integration. So you evaluate as x goes from 0 to 7. Okay. I'm just going to piggyback off of that. Let's see. Let's quick check. I usually leave as an exercise. This is the one with the table, right? I thought the last one was going to be the table. This one is honestly the same as what we just did. You just have to keep doing integration by parts. When you experience that thing of having to do integration by parts several times, like for instance, you would let your u be this guy, and your du is going to be like 3x squared. And so basically, every time we do integration by parts, this term, the power is coming down and down and down. So instead of writing it out, we can use a table. So when we try to do integration by parts in this problem, you'll notice a pattern. Using tabular integration can greatly simplify work, right? So F and repeated derivatives, the sign of the product, and E. G and repeated integrals, right? So then they just, so again, like, because if we start with x cubed, that derivative is 3x squared, but then that derivative is 6x, and then 6 and then 0, right? So what? So then with the sign of the product, I'm thinking that's coming in UV. Yeah, basically from the UV part, right? Let's kind of keep going. Okay, so then add the products along the arrows, making the alternating sign changes to obtain, let me see. So then this guy, and I think the signs just alternate right here, I think. I would have to kind of like sit with it and think about it to confirm that that's actually the case. So then x cubed, e to the x, then it's minus, you see the 3x squared, and then plus 6x until you get down to there. So it says add the products along the arrows. Let me see. Okay. Add the products along the arrows, making the alternating sign changes. So x cubed was positive. Okay. 6, did they have a 6e to the x? Okay. That's fine. Okay, that was an adventure. Right? Because like if you try to do that one straightforward, you were gonna have to do integration part parts like 3 or 4 times. Yeah, it's definitely best to just do one section a day because this stuff is exhausting. It's mentally exhausting. Okay, so but yeah, we saw how we produced that from the tabular form, but it was all based on this first term, just kind of whittling down every time we did integration by parts. So integration by parts formula is the reverse of the product rule for differentiation, right? The choices for u and dv should be such that the integral v du is simpler than the original integral. If this does not turn out to be the case, other choices should be made. Tabular integration is useful in cases where repeated integration by parts is necessary. Right? Okay. So we got through that. We did the best that we could. I'm scheduled to meet with you guys in about 10 minutes. I am totally burnt, so we're going to see how that goes. I might just kind of jump into the homework. Let me see as far as announcements. So at this stage, at this moment in time, this concludes the last of the new material for calculus for business, right? So what that means is with this, we have officially ended chapter 4 on integration and the last of the new material. So then next week we're going to be ready for exam 2 over chapters 3 and 4, right? So the last few lectures, I think the lectures for this week and maybe one from last week, it's on my channel. I just need to put it into the playlist. So you may or may not have found it, but I'll just be updating that shortly. Right now, I kind of struggle with those last questions because I went on and did 4.5 and 4.6 lectures kind of back to back. So by the time I got to the end of the 4.6, I was like mentally exhausted. But we can talk about it. So with that, I'm going to let these recordings kind of persist. And with class time, I'm thinking that we can kind of just start working through the homework, and I'll revisit some of these notions and ideas, and we'll work through as many homework questions as we can. Okay. And with that, we're going to end the session here. And from one beautiful mind to another, enjoy the rest of your day. Okay, guys, take care. Peace.